Here we're going to look for testing for soluble halide ions. And the soluble halide ions we're going to look at are chloride ions, bromide ions, and iodide ions. And we can test for the presence of these soluble halide ions by adding acidified silver nitrate. Silver nitrate has the formula AgNO3. Now, when these halide ions react with silver nitrate, they do so according to the following equation. This is where we need state symbols. So the halide ions are usually in the form of a sodium salt. So NaX, maybe something like sodium chloride, sodium bromide, or sodium iodide. And again, it's soluble. And then when these soluble silver ions meet these halide ions in solution, they join together to form this insoluble silver halide. So we've got a solid state symbol there, and we also get NaNO3. And I'm hoping by this stage we are confident in writing down the correct ionic formulae. Now, what we have now is we've got nitrate ions in solution in my reactants, nitrate ions in solution in my products, sodium ions in solution in my reactants, sodium ions in solution as my products. The sodium and the nitrate ions are spectator ions, and we can remove these spectator ions and write then an ionic equation for this reaction. And that gives us the following, which is an important equation you need to remember. Now, what would we observe? What would we observe in these reactions then? And I'm now going to include F-. What would you observe if we added acidified silver nitrate to a solution containing these ions? Well, firstly, the fluoride ions would give you no visible change. There is no positive test for fluoride ions using acidified silver nitrate, and that's because AgF, silver fluoride, is soluble, so you will not get this solid precipitate formed, so there'll be no visible change. When chloride ions react with acidified silver nitrate, you observe a white precipitate, and that white precipitate is silver chloride. Bromide ions react to form the cream precipitate of silver bromide, and iodide ions react with acidified silver nitrate to form the yellow precipitate of silver iodide. Now, why do we acidify this solution? We acidify this solution first. Now, the reason is consider I've got a test tube of an unknown colourless solution, and I want to see if there are any halide ions present. Now, let's consider that there are carbonate ions in there. You don't know that, but let's just say that there are carbonate ions in there. And I want to test to see if there are any halide ions present. Now, if I add silver nitrate solution to a solution which contains carbonate ions, for example, you would get a yellow precipitate. And you may think, well, I've got a yellow precipitate, so I've got iodide ions. But there is a problem, because when you do react silver nitrate with carbonate ions, you would actually get a solid silver carbonate. which is yellow precipitate. So you get what we call a false positive. It gives you a positive test, which is actually false. What we can do then to get round that is we add acid. We add hydrogen ions. And them hydrogen ions are in the source of those hydrogen ions is nitric acid. Please be aware this has to be nitric acid, not hydrochloric. Hopefully you can see what would happen. If you had hydrochloric acid, you would add chloride ions into the solution, and when you add your silver nitrate, yes, you would get a white precipitate because you've got chloride ions in there. But the chloride ions are actually from the hydrochloric acid, not any present in the original solution. But if you add hydrogen ions then, and then you add silver nitrate, that will remove any carbonate ions which may be present according to the following equation. So you add hydrogen ions, that will react with any carbonate ions, and that would form carbon dioxide and water. And actually what you'd observe, if there are any soluble carbonate ions in there, you'd observe a fizzing due to the formation of this gas carbon dioxide. So we add acid to remove any soluble impurities like carbonates. Other impurities would include hydroxides as well, and hydroxides can be removed by the following equation. So that would remove any soluble hydroxide impurities. Silver hydroxide would also give you a precipitate. Now, we can confirm the presence of these halide ions by looking at another couple of tests. And that's the reactions with dilute and concentrated ammonia. So what you usually do is you've got your solution of, for example, it contains chloride ions. You've added your H+, and then you've added your silver nitrate. What usually happens then is you will form a precipitate of silver chloride. What you usually do then is you separate that into two separate test tubes, and you test this one with dilute ammonia and then this one with conc ammonia. So my other test is with concentrated ammonia. So that's what we get. We've got my silver halide, and once I've got my silver halide, I basically separate them to two different tubes, and then I add dilute ammonia to one of them and concentrated ammonia to another and record my results. Now, with dilute ammonia and chloride, it would cause that precipitate to dissolve, and the same would happen with concentrated ammonia. And it does so because of the following reaction. So the solid silver chloride reacts with the dilute ammonia or concentrated ammonia, it doesn't really matter, you get it's the same equation, and you get the following product, which is something called a complex. But the key is that is now soluble and in solution. Now, if you do the same thing here, but this is now AgBr, what you'd find is with the dilute ammonia, the precipitate does not dissolve, or it only very partially dissolves, but with the concentrated ammonia, you would see the precipitate dissolve. If you do then the same process with the AGI, you would actually observe no visible change with both concentrated and dilute ammonia. So you can see, adding dilute and concentrated ammonia, we get a unique pattern of results which will confirm the presence of either chloride, bromide or iodide ions. And that there is how we can test for halide ions.